Okay, in this video we're looking at inverse trigonometric functions or inverse trig functions. Now, the first function that we're going to look at is the inverse sine function. Okay, so we're looking at the inverse sine function. So we're going to look at the graph y equals sine x. Now I'm going to highlight that graph here. So here is the graph, the sine x curve, y equals sine x. Okay, you should be able to see that. I'll just get a bit closer there. Okay, so y equals sine x is highlighted yellow. We've got the line y equals x. I'll just make that orange. So y equals x, here is the orange line. And if I just turn the page sideways, remember for the inverse function we reflect in the line y equals x, and I'm going to draw the inverse sine function in pink. So the inverse of that sine function, I'm just doing it by reflecting in the line y equals x. So that one's in pink. That's the inverse sine function, because these points, that would be the same. This point becomes that point there is there, etc. Now, we can see that this inverse sine function, which is labelled here as x equals sine y, okay, so we've got x equals sine y. The yellow one, the original function, is y equals sine x. We can see that y equals sine x does not pass the horizontal line test, and so therefore x equals sine y, which is the inverse function, will not pass the vertical line test. So this x equals sine y is actually an inverse relation, not an inverse function. So, however, if we restrict the domain of y equals sine x, we will be able to obtain an inverse function. So remember, you need a monotonic increasing or decreasing curve. So if we go, say, from 0, we know that this is pi here, which I'll do that in another colour, okay? So here I've got, on the sine x curve, I've got pi because here is 2 pi, and that's 0, and this is negative pi. But even if I go from 0 to pi, this does not pass the horizontal line test. And if you look at the inverse of this bit, it's this yellow bit just there, and that doesn't pass the vertical line test. So I can really just go from 0 to pi on 2. But there's no reason why I can't come back here as well. Remember, I'm just looking for monotonic increasing or monotonic decreasing curve. So just to be closest to 0, if you just watch what I'm tracing here, this is all monotonic increasing. So I can really go from, if I go from negative pi on 2 to positive pi on 2, if I restrict the domain of sine x from negative pi on 2 to positive pi on 2, an inverse function will actually exist. And that inverse function, I probably shouldn't have highlighted the other one so soon, but the inverse function will be just from here, where I'm highlighting, down to there and stop. So I'm going to do that down on the graph below. So if I'm just taking the original function from negative pi on 2 to pi on 2, and if I draw the inverse here, the inverse function will be a function actually, or the inverse relation will be a function, provided I don't go beyond those points which correspond to these, okay? So yes, we can restrict the domain of y equals sine x so that the inverse function exists. So we can restrict it from minus pi on 2 through to pi on 2. And is this domain the only one that gives an inverse function? Well, we could also do the domain from pi on 2 to 3 pi on 2. That would give an inverse function. Okay, that's monotonic decreasing just in that section, say from pi on 2 to 3 pi on 2. I could also go from minus 3 pi on 2 to minus pi on 2. That's monotonic decreasing as well. However, because, you know, often when we draw curves, we like to start from 0 or around 0. So this seems like the most sensible one to choose, from minus pi on 2 to pi on 2. So we're going to draw that all again down here. So the inverse function, or the inverse sine function, is written as y equals sine to the minus 1x. Now, as we said, if we restrict the y equals sine x to a monotonic increasing curve, say here, now we know that if we just go back up here, the amplitude here is 1, and down here we've got -1. So we know that the range, so here for this sine curve here down here, same curve, okay, the domain, if you restrict it to minus pi on 2 to pi on 2, then the range, okay, the range will be from -1 to +1. The y values go from -1 to +1. So of course the inverse sine function will have swapped domain and range values. So if we draw the dotted line y equals x, now if we draw the dotted line y equals x, and let's say I'm trying to draw it here and you're trying to work out where this line y equals x is, remember pi is 3.14, so pi on 2 is going to be about 1.57, so 1, so this is, sorry, so this point is about 1.5 something, one sec. So drawing the line y equals x, it'll probably come up through here somewhere, okay? So 1 would probably be here and your dotted line would be here and the reflection would go like that. Now it is a little bit hard to draw on that because see, this is not drawn to scale. This distance of pi on 2 is about the same as that, or even shorter than that distance 1. So it's actually not a really good one to draw y equals x on. But what we'll do, we know that if y equals x was there, that the curve would be, I mean, I'll just draw it roughly, okay? If we've got the dotted line y equals x and we reflect, we know that the inverse is going to be the other shape, okay? Going back like that, which we can see down here. Now, if we've got pi on 2 and negative pi on 2 there for the domain of the inverse function will be the 1, -1. What's on the y-axis will be on the x-axis here for the inverse function, and what's on the x-axis here will be on the y-axis here for the inverse function. So this curve here is the inverse sine curve, okay? And notice its domain is the range of the other function. So its domain is the range of the sine curve, and the range of the inverse sine function is the domain. But of course you swap the x with the y, okay? And you have to know the shape as well. So that's the first function that you need to know, okay? So the best thing to do is I would draw my sine curve and make sure you don't start from 0, that you start from before 0. You'll see the bit that's monotonic increasing. You'll know that that goes from minus pi on 2 to pi on 2, and you know that the amplitude is 1. So therefore, because you know you're 1 and -1, you know for your inverse sine, this is 1 and -1, and your domain will become your range here, okay? Now, if you can, please just make sure that you've taken notes on that, drawn each curve, written the domain and range for each of the sine curve, the restricted domain sine curve to make it monotonic increasing, and notes on the inverse sine function as well. Now for the inverse cos function. Now this time I'm only going to highlight where the monotonic increasing or decreasing is. We'd like to start from 0 if we can. This is all monotonic. We know that the cos curve goes like that, okay? So cos curve, it's still monotonic decreasing, and I'm going to stop here because then it becomes monotonic increasing. So that's going to be the domain that we would like to use. If we did continue, it doesn't pass the horizontal line test, the original function, so therefore the other function is not going to pass the vertical line test. Remember, here is the cos function, all there, and this is the inverse cos function. So let's look at our values. We've got 0. This over here is 2 pi for one complete period. This here is pi. And this here is pi and 2. So we are just going to use the reflection here does not represent a function. If we reflect, here's our line y equals x. If we turn it sideways, we can see that the cos curve here is reflected there, okay? And we can see that this bit here is reflected there, okay? So we're going to restrict to 0 and pi this time because it's still monotonic decreasing for that section. So can you restrict the domain so that the inverse function exists? Yes. You can restrict it from 0 through to pi. And is this domain the only one that gives an inverse function? Well, no, it's not. I could also go from 0 here to -pi. That's monotonic increasing. Or I could go from pi to 2 pi. That's also monotonic increasing, okay? So it's not the only domain. There are other ones, provided that they're monotonic increasing or decreasing. So remember, the amplitude of the cosine curve is 1, okay? And down here we've got -1. So let's look at the cos curve on its own. So if we restrict the original cos curve to restrict the domain from 0 to pi, as we said, we're not going to come back up, because then it won't pass the horizontal line test, and then it won't be monotonic decreasing. So the domain of this is 0 to pi, and we can see the range is 1, -1 is less than or equal to y, which is less than 1, less than or equal to 1. So you want to write y equals cos x here and write down its domain and range. Now, if we draw the line y equals x and reflect in that, sometimes a bit tricky to draw, and this bit would come back down here. But what we can do, let's just swap values. Swapping values is actually the best thing to do. I should have told you this with the other graph, but here I've got, sorry, I should have told you this before. This here is the point 0, 1. So therefore on the inverse function you've got 1, 0. This here is the point pi on 2, 0. So on the inverse function, you've got 0, pi on 2, okay? This here is the point pi, -1. So on the inverse function, you've got -1 pi, which you can see up there. So that really is the best way to mark out your points. It's really easy to draw the original function. Remember, swapping the x and y values, don't forget to do that. That will then give you the shape, okay? So coming back to this one, okay, coming back to the sine curve, let's just do the same thing here. Here we've got, for our points, notice we've got up here, we've got pi on 2, sorry, we've got pi on 2, 1, and on the inverse curve, on the inverse function, we've got 1 pi on 2, okay? Down here, we've got -pi on 2, -1, and on the inverse function, we should have -1, pi on 2, which we do. And here we've got 0, 0, and there we've got 0, 0. So don't forget to do that. Just swap your x and y values at those endpoints as well. Okay, just remembering the shape is going to be reflected in the line y equals x, and here as well. This one's a bit harder to do. So, but you do know it goes from 0. So here, domain 0 to pi, here, range 0 to pi. Okay, so going backwards like that. If you mark out these points, that's really the only thing that you can do with that, okay? So just make sure you write your notes here, your inverse cos curve, what the domain is, which happens to be the range of the other one, and the range is the domain of the original function, okay? So make sure you write all this out. Next one we're going to look at is the inverse tangent function. This one's, looking at this diagram, is going to be a bit harder to see, so I'm going to do some highlighting. Here is my original function about the y-axis. Remember, y equals tan x. Actually, I might just draw my own one. Remember, with y equals tan x, it goes like this, and that's monotonic increasing. And remember, this is 0, and this is pi on 2, and this is -pi on 2. So for the curve y equals tan x, if I start doing more than one period of the curve, it's not going to pass the horizontal line test. So we're just going to take the one about 0. So can you restrict the domain so that an inverse function exists? Yes, you can, between -pi on 2. But this time we don't put less than or equal to, because this y equals tan x curve does not actually touch the line x equals pi on 2 because it's an asymptote. So please do not put less than or equal to. It's just less than. So x is greater than -pi on 2, which is less than pi on 2. So please be careful with that. It's less than, not less than or equal to, because of the asymptotes that we have. Okay? And this is not the only domain that gives an inverse function. I could have taken I could have gone from pi and 2, I think, to 3 pi and 2, or any of the others as well. Okay, so let's have a look. So the inverse tangent function is written as y equals tan to the minus 1x. Here is my original tan function, y equals tan x. If we restrict the domain to negative pi and 2 to pi and 2, notice there's no less than or equal to signs because of the asymptotes. Well, we can see that the range is all real y. So domain negative pi and 2 less than x less than pi and 2, and the range is all real y because there is no restriction on the y values up there or down here. So of course with the inverse tan function, all of this is swapped around. So with the inverse tan function, the domain should be all real x this time, and it is, okay? And the range this time will be from negative pi on 2 through to pi on 2, noticing that we do not put less than or equal to signs. So in the original function, x equals negative pi on 2 and x equals pi on 2 are asymptotes. So therefore in the inverse function, y equals, that should say pi on 2, and this one's negative pi on 2. So y equals pi on 2 and y equals negative pi on 2 are asymptotes, okay? Now, if you did draw the line y equals x and reflected the curve, the shape would change, okay? So it would go like this and like that, and you can see that shape there. So you've got to be able to know the shape as well. Okay, obviously that's like that, the other one will be like that. Okay, so that's your function, inverse function for tan, y equals tan to the minus 1x, with the domain and the range. Please be careful, there's no less than or equal to's in those domain and range for either the original function or the inverse function. Okay, now how are you going to remember the shapes? First one goes like this. The sine one, of course, we did first, then cos, then tan. Sine ones like that, they're all a bit different. I think of it as almost like the y equals x cubed graph. And the other one goes backwards shape, but we know that that it goes from 0 to pi, so it's lifted up here. Okay, that's because the original cos curve has a domain of 0 to pi, so the range of this is 0 to pi. So first one, well, it's like y equals x cubed. The other one's, I suppose, like y equals negative x cubed, but moved up. And the other one, the last one, the tan one, we know that we've got the asymptotes that way. And if you know what the original one looks like, if you're reflecting back that other way, it goes that way. Okay? You'll have to come up with little tricks to try and remember the shapes. Examples, find the inverse tan of 1. So we just start by saying let y equal tan to the minus 1 of 1. Now, we've seen this before. For example, if y equals tan to the minus 1 of 1, this is what you enter into your calculator, for example, if you are solving the following. If you're trying to solve tan of y equals 1, on your calculator you go or tan theta is 1, for example, you go, to work it out, you go inverse tan, so shift tan, 1 equals, and you get your answer. So if you see y equals tan to the minus 1 of 1, we're just saying what angle, tan of what? Tan of what will give me 1, and we know that that's tan 45 or tan pi and 4. So therefore y equals pi and 4. Now what you need to do whenever you get any of these answers, it's fine with the quadrant 1 answer here, but you've got to be aware of what the domain of all of the curves are, but the range of what all the curves are. So remembering, I'm just going to have a quick sketch of all the curves up here because you should know what they look like. Remember the cos, the sine, inverse sine function looks like this, sine to the minus 1 of x. Okay, instead of it being 1, negative 1, they're here. 1, negative 1 is your domain. Remember you've got pi and 2, negative pi and 2 for your inverse sine function. Remember your cos one is the opposite shape, but that one starts up here and finishes down there. That again is 1, negative 1, but this is 0 and up here is pi. So that's your inverse cos function. And remember your inverse tan function has the vertical, not that vertical, the horizontal asymptotes, and that one looks like this. And these are, its range is from negative pi and 2 to pi and 2. for your inverse tan function. So you've just got to keep these in mind when you're coming up with these solutions here. So we've just got them up there. So pi on 4 does lie between negative pi on 2 and pi on 2. However, if I was asking you to find, so example 2, to find the tan, inverse tan of negative 1, okay? Now we say, again, so let y equal tan to the minus 1 of negative 1. So tan of y is equal to negative 1. We know that we've got two solutions here, all stations to central. Tan is negative in quadrant 2 and quadrant 4. However, if we do the quadrant 2 answer, which is between 90 and 180 degrees, that means that it'll be bigger than pi on 2, so it doesn't fit in that range. So therefore we have to take the quadrant 4 solution. So therefore y will be in quadrant 4, we've got negative 45 or negative pi on 4. So with the negative ones you need to be careful, okay? With the positive ones, they'll always pretty much be they will be in quadrant 1, but with the negative ones you've got to be careful, except for when cos is negative, and we'll do one of those in a minute, because when cos is negative you have to go to quadrant 2 because cos is positive in quadrant 4, but notice you can go up to pi, which is 180 degrees, so that's fine with the cos being negative, okay? Just some more examples. Example 3. If you're trying to find or evaluate the inverse sine of negative 1 on root 2, we let y equal inverse sine of negative 1 on root 2. Therefore, sine of y equals negative 1 on root 2. Now, we know that this is pi on 4. However, quadrants 3 and 4 are where acute angle is pi on 4. But quadrants 3 and 4 is where sine is negative. So we'll have to be able to fit into the restricted range of pi on 2 to negative pi on 2, which is basically quadrants 1 and 2 here. Our only option is the quadrant 4 result, which is y equals negative pi on 4, which is negative 45 degrees, just here, okay? If they're my axes, okay? All right, looking at another one. Let's look at cos to the minus 1 of negative root 3 on 2. So we're going to let y equal cos to the minus 1 of negative root 3 on 2. So therefore cos of y equals negative root 3 on 2. Now all stations to central, cos is negative in quadrants 2 and 3. This goes up to pi, so this is allowed because the range of the inverse cos function is from 0 to pi. So therefore we'll have our quadrant 2 result here. Cos of 30 is root 3 on 2. 30 is pi on 6. Okay, so, but it needs to be the quadrant 2 one with pi on 6 in there. So that would be 5 pi on 6. So we can see here our acute angle is pi on 6. You can either write it as y equals pi minus pi on 6, which is 5 pi on 6. You can write it like that if you want, okay? Or we know if that's 30, this is 150. So that's 5 lots of 30, which is 5 times pi on 6, okay? Remembering that we have a restricted, because the range of the sine to the minus 1 curve is from 0, sorry, the cos, inverse cos curve, the range, sorry, is from 0 to pi, okay? Or I can just write 0 less than or equal to y less than or equal to pi. But remember, we would be sketching the curve y equals inverse cos of x. See some questions written like this. Evaluate the sine of the inverse cos of negative 1. Now, in other words, what cos of what will give you negative 1? Now, we can actually see it up on this cosine curve that cos of pi, the inverse cos of pi will give me negative 1, but we can set it out like we were before. Okay, so if I let y equal the inverse cos of negative 1, therefore cos of y equals negative 1. Cos of what is negative 1? If I just draw a cos curve, for example, just making sure it's monotonic, we know it goes from 0 to pi. Here we've got pi, so therefore y will be pi. So therefore here I'm really just evaluating, therefore the sine of the inverse cos of -1 is the same as saying the sine of pi, and we know that we're now talking about the normal sine curve, okay, because there's no inverse sine there. So sine of pi, this is pi on 2, sine of pi is just 1, okay? We'll find the exact value of the cos of 2 tan to the -1 of -1. Now let's just let alpha equal tan to the -1 of -1. So therefore tan of alpha equals -1. Now we know tan is negative in quadrants 2 and 4. We know that tan of 45 is 1. But because we've got a restricted range of negative pi on 2 through to pi on 2, we have to take the quadrant 4 result. So therefore alpha will be negative pi on 4. So therefore my question, cos of 2 tan to the -1 of -1, now becomes cos of 2. Now I know tan to the -1 of -1, I have let that equal alpha. Okay, so that's cos of 2 alpha, which is the cos of 2 times negative pi on 4, which is the cos of negative pi on 2. Now this is normal cos of negative pi on 2, so I can do a little sketch there. This is my cos curve. Well, that's, here's negative pi on 2 there. Cos of negative pi on 2 is 0. Okay, that is, I'm now talking about a normal cos of whatever that is. So it's cos of negative pi on 2. You're just talking about the normal cos curve there. Evaluate the inverse tan of root 6 sine pi on 4. Okay, we should work out what this root 6 sine pi on 4 is. So I can just work that out because that's just a normal function. So this is the same as tan to the -1 of root 6. Now sine of pi on 4, that's sine of 45 degrees, which is 1 on root 2. So this is just the same as the tan to the -1 of, now root 6 times 1 on root 2 is just root 6 divided by root 2, which is root 3. Now if I let that equal alpha, or tan of what is root 3? We know it's tan of 60 is root 3, so the answer will be pi on 3. But you can now go let alpha equal tan to the -1 of root 3. So therefore tan of alpha is root 3, and we know that alpha therefore will be pi on 3, which is 60 degrees. Remembering that it has to lie between negative pi on 2 and pi on 2, and it does. Look, the positive ones, quadrant 1 ones will be fine. So therefore the answer to this is pi on 3. Okay. Evaluate this function here, inverse sine of 2 sine negative pi on 6. Again, we can just work this bit out. Okay. So that's equal to sine to the -1 of 2 times. Now if this is sine of -30, it's quadrant 4. Sine of 30 is a half, so it'll be -1/2 for quadrant 4. So that's the inverse sine of 2 times -1/2 is -1. So if we let y equal all of this, okay, therefore we're looking for the sine of y equals -1. Now we're looking for a normal sine curve. You've got to be careful, because you can't go over here to 270. It's got to come back here to negative pi on 2. That is because, so therefore, because it's the inverse function here, inverse function of inverse sine of -1. So I know I am drawing the normal sine curve here. Instead, you could actually draw the inverse sine if you want. So I probably shouldn't do that because some people might get confused. If I draw the inverse sine, remember we said it looks like the y equals x cubed graph. And -1, remember this is 1, -1, so this is negative pi on 2. Sorry, that's not -1 there, it's negative Yes, it is. It's negative 1. And this is negative pi on 2 here. Okay, and that's pi on 2 there. Okay, so therefore y equals negative pi on 2. Okay, if you do want to look at the original sine curve, you've got to remember that that's the piece of the original sine curve that we take, where this is 0. We don't take this other bit over here. Remember, we only want the monotonic increasing part of the original sine curve. So sine of what gives you negative 1? It has to be negative pi on 2, which would be here. Okay, so you can look at either the inverse function or the original function, but if you're looking at the original sine curve, remember just to take the bit that we looked at when we decided. You need to look at the restricted domain of it, basically. A lot of examples, but just another one here. Evaluate this, the inverse tan of 3 tan 7 pi on 6. Now just be careful here with the 7. Well, you can draw that. This is still just the normal function, so just do it as normal. There's pi. This would be 7 pi on 6 over here, which means that this little angle in here is pi on 6, because you've got pi plus pi on 6. So we're looking at tan in the third quadrant, tan of 30 basically, which is 1 on root 3, and it's positive because all stations to central. Tan is positive in quadrant 3. This is still just the normal function I'm looking at, not the inverse tan yet. So that will just be inverse tan of 3 times 1 on root 3, and that happens to be positive, which is the inverse tan of 3 over root 3, which happens to be inverse tan of root 3. Now, inverse tan of root 3, that's a quadrant 1 angle, it's positive. Tan of what? So you can let this be y. So therefore tan of y is root 3, therefore y is tan of 60, which is pi on 3. Okay, remembering the domain for the tan, inverse tan function, because that's what we're solving, the inverse tan function. The domain for that is from negative pi on 2 to pi on 2. Okay.